Welcome back to Battery Generation, your podcast on electromobility and European battery research. Today, we finally have the chance to talk to a leading expert on solid-state batteries. Hello, Professor Jennifer Rupp from Munich, Germany. Nice to have you here.
Hi, Mr. Rosen. Very nice to have me invited.
Let me introduce you to our audience, Professor Rupp. You are a professor at the Technical University of Munich, a visiting professor at the Massachusetts Institute of Technology, and Chief Technology Officer for Battery Research at TUM International Energy Research. Solid-state batteries have been announced multiple times already. For lots of researchers, solid-state batteries are the holy grail since they promise an outstanding energy density. But lately, honestly, we get the impression that the current lithium-ion batteries with liquid electrolytes are being developed at a much faster pace than solid-state batteries. We might be wrong on this, but we ask ourselves, will we even need solid-state batteries after all? And will we probably never see them, Professor Rupp?
Thank you so much, Patrick. This is a very valid question, right? So overall, I think we can say that the lithium-ion battery market is progressing. However, there are certain limitations in the energy density that you have overall, where a solid-state battery could give you the 30% higher increase in energy density. And if we look at the market price, I think that's a very important thing to compare, right? Then you would find the lithium-ion battery at being at around like 700 watt-hour per liter with $120 per kilowatt, going down to 90 roughly in the next 5 years. And the solid-state battery currently being higher in price tag, right? So this is right. So you're about like a factor of 3 higher. However, this is supposedly going down, and the increase in energy density is so high with 30% that I think there's a very high likelihood on your question that we will see solid-state batteries or that components thereof will be integrated later for hybrid batteries in various forms. So I think this is a very crystal clear future that this is going to happen, impacting, I think, as well hybrid and possibly full solid-state batteries.
Well, then let's take a look back on 2008 until 2020. The volumetric energy density of lithium-ion batteries increased more than 8-fold between these years. And again, what do we need solid-state batteries for if this trend continues? I mean, wouldn't you compare these two technologies with another after all?
I think the trend is predicted not to continue. It's going in a stagnation. So if you look in lithium-ion batteries, then they're roughly, I think about 300 watt-hour per kilogram, 750 watt-hour per liter. This will increase maybe a little bit, but more like in the maybe like 10-20% range, and that's it. Whereas in solid-state batteries, just by a switch of materials and enabling with lithium and other materials, is much higher energy density. You have the perspective to reach double of the gravimetric energy density and actually 30% plus of the volumetric energy. And this is actually, I think, a very steep curve. So currently, I would say that it is not to be expected that the growth rate that has been seen in the volumetric energy density of lithium-ion battery is continuing in the same slope. It's not.
That's very interesting to hear. Of course, we get these announcements from CATL and Amprius. They recently announced a condensed battery with an energy density of 500 watt-hours per kilogram. And I asked myself, are we there yet? Are these solid-state batteries by definition, or is that slightly something else?
I would think it's likely that it's having some solid-state battery components that is still, I think, to be confirmed and to be seen. But it's, I think, a good sign. It means that leading companies are actually going in this way, right, and are facilitating technology that is relevant from solid-state battery materials, I think, in parts of their battery designs. So I think it looks very, very promising, actually. Yeah.
I have read something that was already 4 years ago about these blue cars in France. Bolloré, I think, was the name. I asked myself by then, why have these batteries not been developed, further developed up until now?
Yeah, so I think it has to do techno-historically also with the fact when you look back, how are some of the most prominent solid-state lithium conductors, may it be in sulfide or in oxide, it doesn't matter. When have they been proposed, and then how long did it take the field to optimize those materials? And you can clearly say this is a development of the last 10 years, right? And it needs then a certain traction for many scientists and engineers to jump on this topic. And that is, I think, the developments that we're currently into integrating that into products, bringing and spinning that out to the market. So that is, I think, currently the development. But I would say 10 years ago, there has been not even, I think, enough processing know-how, how to make, for instance, those materials and really good layers, define good interfaces to actually later have a good energy storage and exchange actually here. Yeah.
Well, then let's jump into the cell chemistry. Would you please at first distinguish between these terms all solid state battery and almost solid state battery? What is a solid state battery by definition?
So I think there are these different types. So an all solid state battery, you can define of having no liquids ideally inside. So it has all the components being a solid state. And what it classically defined is that you have a lithium-based anode, a solid state electrolyte that can have lithium ions migrating over defects or over random walk in the material. And then you have a cathode-based component. So it forms like a solid anode electrolyte cathode interface. And in this all solid state battery, I think what is a huge advantage is because you have no liquids inside, you can use actually solid state battery electrolyte which large electrochemical windows, which allow you to really profit from these high energy densities towards pure lithium. Now, in a normal solid-state battery, you could say you use a little bit the best of both worlds, right? In a classic lithium-ion battery, you have up to 25% of a liquid. In a solid-state battery, it's 0. Now, the almost solid-state battery I would define as such as having lithium, a solid-state battery electrolyte, and then a cathode where you have, for instance, partially wetted interfaces that help later in the lithium diffusion over the interface. So that one you would have maybe something like 5 to 10 weight percent of a fluid, to just facilitate the transfer, but use the benefit of having pure lithium enabled by the solid state stable battery electrolytes that you have inside.
And can you also distinguish between these types of electrolytes? I've heard about ceramics, I've heard about polymers, and even sulfur-based electrolytes. Is there huge differences?
Technically, you can say that it's the world of ceramics, which would entail oxide-based solid-state battery electrolytes and also sulfide-based solid-state battery electrolyte. So ceramic is defined as an inorganic chemistry, right? So it can be both, right? And within this share of ceramics, what they have in common is that they are solid-state compounds that you try to densify as a layer. Now, between oxide and sulfides, there's still some differences, like, for instance, a changing electrochemical stability window, which is for some of the oxides much larger than for the sulfides. But then on the sulfides, you may have a faster diffusion, the solid-state case. In a polymer-based material, you have polymer chains that form kind of like a polymer coating that you have. And there, very often, you have actually the lithium going through a random walk. So it's a very different migration work. And also their electrochemical stability window and the overall lithium conduction may change. And if you reflect further, they obviously also differ in their mechanical stability and in making good interfaces, towards the cathode and the lithium, where they have different wetting abilities between the ceramics and the polymer. Yeah.
We have often talked about these solid-state electrolyte interface in current lithium-ion batteries in this podcast. Could you please explain to our listeners how that works in solid-state batteries in general? Is there something like an SEI even?
I think that it's quite common when you bring two solid-state materials together. Let's exemplify. You have a composite cathode. So this would mean you have a part which is a cathode phase, which could be lithium cobalt oxide in this example, and you have an electrolyte phase, which could be lithium garnet, just for the heck of the example. Now, if you bring them together, these two phases may have very different positive effects actually that you want to join in. On the one hand, you want to have, let's say, some electronic conduction, and you want to have a huge filling in the cathode of the active cathode phase, but you need also some ionic conduction. Now, if you bring both materials together, you need first to find a way that the adherence is very good, that you have good mechanical stability, and the cathodes start to swell. Yeah. So it's not a static material you bring in, whereas the electrolyte is more not swelling, but it can be a good support structure. And if you think about the charge and mass transport, that has several implications. As of, in a liquid phase, you would have covering all over. If it's solid state, it's just the contact points that you have. And the lithium, as it migrates over defects often, is a little bit more inhibited to do so. So you need a certain activation for this to happen at the interface. And that is, I think, some of the holy grails of finding the best optimization between good transport at the interface as they form some form of a little capacity at the interface, which they shouldn't ideally, but in real life they do, yeah. And then also kind of like having as much lithium transfers through that, and overall having a very low kind of like interfacial resistance. That's what you want. That's what you optimize for as an engineer. Yeah.
There's one huge difference in one variant, so to say, of a solid-state battery. We have heard about an anode-free cell. How does that work? Our listeners are very used to the traditional function and setup of a battery with an anode, a cathode, separator, and electrolyte. How does a cell without an anode look like?
Yeah, it sounds kind of like odd. I may admit that, and maybe the terms are also kind of like not very well placed, but that's how it's named right now. So in this anode-free design, what you would have is, for instance, a metal grid, or you could take a copper grid, for instance, right? And you could use the ability of the solid-state battery electrolyte and the cathode to just internally kind of like have lithium transfer through the electrolyte plate and go back, actually. And in doing that, you don't have, so to speak, an active anode. Yeah, you kind of like form and deform it all the times. And that has, of course, obviously several advantages and disadvantages later on the cell life. Yeah, but it is an option to operate like that. That is currently under discussion in hybrid and also in solid state battery designs.
Really interesting. At this point, let's talk about mass production. We'll talk about the stability and safety of solid-state batteries in a while. I picture a production site, let's say the part of assembling the cell, pretty difficult when filling in the electrolyte, the liquid electrolyte. Isn't that much easier with solid-state batteries to mass produce these cells, or am I mistaken?
The answer is yes and no. So here's a digested answer. And what I will say, I would say, I think there's very good industry standards, and the field has come extremely far in making liquid-based electrolyte lithium-ion batteries, right? And there's a certain sequence of assembly. It's actually a quite beautiful process because you have a polymer separator, and you just can assemble by density, cathode, your anode powder, and your liquid type electrolyte or a salt. So it's actually quite straightforward in putting that in a small capillary. Now, in a solid-state battery, what seems on the first sight to be very easy is everything is a solid, right? So that's beautiful. You have zero liquid in it. And you could say, well, you just assemble your cathode, your electrolyte, and your anode, right? However, here's the trick. So to later, and that's something we should remind ourselves, in an electric vehicle, you need a 30 by 10 square centimeter area that has to be crack-free and homogeneously coated, yeah? 10 by 30 square centimeter. And this is for any ceramic, if I take that as an example, still quite a challenge, yeah, because to make tapes, for instance, the size that are crack-free, or to make also like towards pressure homogeneous sulfide electrolyte coatings isn't as easy as it seems. And it needs also a certain pressure for the latter, for instance, during operation. These are things that you don't have in the initial assembly of a typical liquid type solid-state battery. And you can say there is, if you go on sulfides, the challenge is really to maintain the pressure, to really make sure that on this footprint of the area, this is maintained, and that you have a suitable kind of like array actually here of your anode electrolyte cathode layers. I would say on the oxide-based kind of like designs that you have, there's a challenge is to get a crack-free sintered or otherwise produced electrolyte that it has a good contact later with cathode and the rest. You need less pressure, but that is your challenge. And I would say that these are manufacturing-wise currently the largest challenges. And there is a balance between how you process that and your costs that you are allowed later to cost. So currently, when you look, for instance, what a classic lithium-ion battery electrolyte costs based on a separator and polymer, it's about $1.5 per square meter. Most of the solid-state battery electrolytes are more like $4 to $6 per square meter. And this means also that we have to really examine very carefully what is the best way of processing that, which processes to take, what to ditch, literally, to make that work for the solid-state batteries. But that's roughly where lithium-ion batteries have been a decade ago, right? And that's fair. That's just only fair. And it will go down. I'm very convinced about this.
I was hoping for an easier answer, but that kind of I get the impression that the nowadays sites for building the current lithium-ion batteries can partly not be used for future solid-state batteries. Could you talk on pricing and costs once more? These first solid-state batteries, will they be at a high, very cost level, pricing level?
Currently, I would say they are, realistically. So they are a factor of 2 to 3 higher than the lithium-ion battery. If I just take the electrolyte, it's $4 to $6 per square meter for the solid-state battery electrolyte versus $1.5 to $2 per square meter for any electrolyte you take right now that you have in your lithium-ion battery. So this is the difference. But then on the other hand, you have to say you are allowed to be higher in the solid-state battery electrolyte. If I just exemplify that by 30%, because you gain that energy density. Still, it means that overall this has to come down. What's driving those factors is things like material assembly, like processing. 75% of this cost is just processing. It's not the raw material. So anything that we scientists and chemists and engineers can do to reduce the share of processing costs like pressure, temperature, all of those, is going to reduce later the price in the end. And I think that's the avenues to be explored.
I thought the more lithium you use in a solid state battery, the higher the price. But let's talk about something else first, about the applications solid state batteries will be used for in the first place. So do you think electric vehicles is something to be equipped with solid state batteries, or maybe are we talking airplanes? Are we talking long haul trucks or maybe vessels?
Yeah, I think that is a great question. And I would say for now that solid state batteries are considered by several manufacturers, as well as hybrid batteries using a solid state battery electrolyte, but then with a little share of liquids, are considered in electric vehicles and are pursued, which is exciting. This is very important. To give you an example, even a classic combustion engine car, just if you think about the carbon dioxide footprint, has a 40% higher carbon dioxide footprint than any electric vehicle. If I can increase the range of the car to drive by having a solid state component in by 30%, that's an argument. And I reduce my personal carbon dioxide footprint by 60%. So even the dirtiest battery, the dirtiest that I put in, is fantastic because my personal footprint is so much more improved in doing that in carbon dioxide. Now, will it go in a truck and airplanes? Yes, I think it's very high perspective right now. It depends always whether you're looking, for how much the specific energy is also going to be, how much weight you can carry with yourself. These are considerations. And then what is the range that you have for your application? And within the spectrum, I would say there can be in the portable sector various solutions that can range from, is it better to take a full solid state, a hybrid battery with some liquid in it as well, or even a lithium-ion battery, or another energy conversion or storage scheme? And to have on this a precise answer, we're just going to have to wait a little bit, I think.
Definitely. Nevertheless, CATL from China, they have announced to soon work with aviation companies, with airplane manufacturers for the condensed battery. I'll give you three other manufacturer names. That is QuantumScape, a Volkswagen investment, Prologium from Mercedes or a Mercedes partner, and then finally Solid Power, that is working with BMW in Munich, together with you guys at the Technical University in Munich. So every German OEM car manufacturer already have an investment for solid-state batteries. What can you tell us about the developments and activities of these three solid-state manufacturers?
Yeah, so I think what one can say is that what is exciting is they set on very different materials and technologies. Yeah, so if you think about solid powers, then I think it is public that it's more considering sulfur-based materials for the electrolyte, looking into this direction where the positive part is you can process it all at very low temperature. The challenge is you have to equalize later and maintain the pressure up in the cells. That's for sure what is currently a hot topic there in the field, if you think about sulfides. Prologium is, again, another set of material. They are looking into oxide polymer separators. And in those, they're kind of like looking more at, trying to combine the best of both worlds, so to speak, right? Having a soft matter with, later like oxide-based compounds in assembling the whole cell. So it's kind of like quite flexible, right? So it can be good and difficult to apply later the pressure. Maybe a bit of a down pit on the electrochemical stability window. But I think there is, for each of those, in this diversity of various battery designs, very different pros and cons. And it represents at the very best that the field is divided up to unclear who wins. And I would say maybe that doesn't need to be a winner. It is allowed to have very different concepts that will later lead to different product lines. And for different applications, the one or the other may actually do better the trick. So I think it's very positive that a diverse landscape with these three names exists in providing products.
All right, this is already a very important takeaway message. A solid-state battery is just a term which combines lots of different approaches. But what do you expect from lifespan of the first solid-state batteries? Will they last for longer as the current lithium-ion batteries with fluid electrolytes?
I think some of the solid-state batteries have incredible lifespans, like 10,000 cycles. If you think about LiPo, a material we don't use so much, but actually was one of the first solid-state battery electrolytes seriously put into solid-state batteries and tested really over long lifespans. It's remarkable. It has 10,000 cycles, so that's great, right? The question is how to compete with that. And because it has a stable interface, there has been some competitors, but not too many from a material perspective, Now, towards, I think, liquid ion, this is very promising. It shows you some of the benchmark of where that can go. And I think understanding these interfaces and how to engineer, stabilize them is key. That's what one is on. But it shows you, I think, one end of the benchmark, which is very promising towards lithium ion.
Well, there's another topic we have to talk about, safety of these first solid-state batteries. Of course, everyone is talking about the higher safety, apparently, about these cells. But again, they store much more energy in these cells. So I don't really get this as a non-scientist. There's absolutely no way these cells can explode, can catch fire. That can't be true, right?
Patrick, you're so smart. I think absolutely, right? I mean, if you take a big hammer out, you can kind of like throw it on anything and it will crack, right? At some point eventually. Same with a battery, right? If I were to really do that and put it in the most extreme condition, it will, sure. But on the other hand, I think remarkable remains, you can take, for instance, an oxide-based solid-state lithium electrolyte, and I can have it openly in air, right? And it's not going to inflame because the lithium is stored in some positions within the material and is later kind of like stored on these defect positions quite safely. So I would say that compared to the classic lithium-ion battery, the more you reduce the fluid content the safer you are. Yeah. And if it's more oxide, you have very high temperatures where that was assembled, it's probably going to be fine, right? And I think there is some boundaries in it, and one can always critique it, but I think overall it is safe to say that the solid state battery is safer than the lithium ion battery, I think, overall, in terms of the materials that you put in.
I'm asking that actually for my colleague who, as well as me, followed these announcements from CATL, trying to work with aviation companies to sit in an airplane that is powered by solid state batteries. Of course, the batteries must be 1,000,000% sure to not catch on fire. So that's probably the case where safety is definitely the most important thing for these cells, right?
Yes.
Let's talk about sustainability of solid state batteries. Of course, every cell innovation nowadays has to be sustainable, more sustainable than we see nowadays. The lithium content is sometimes up to 80 times higher in solid state batteries with a lithium anode, for example, compared to nowadays lithium ion batteries. And we are already seeing shortages of lithium in Europe and elsewhere. So my question is, shouldn't we switch to solid state sodium batteries right away? Is that possible?
Yeah, so I think there is a factor of 10 more sodium than lithium available or knowledgeable by what is there as a mining resource. So this is quite comforting in terms of availability. And if you have a little bit of a look on the stock market price, I think the lithium price went up a factor of 4 or something over the last, I think, 3 years. So it's actually quite remarkable. It's raising, yeah. So this would be strong motivator going to sodium. So here is where I think there is also a little bit of a reservation in the field as well. So for sodium, there is still on a cell level some of the voltage window, which is not equivalently achieved. So let's say in energy density, there is great work currently being undertaken, but I think that's something that needs to be worked on further. Yeah. And we will see where that goes. And I think it's very promising to also look into sodium, but also currently realistically working and looking also with lithium.
There's so many more aspects of sustainability, of course, within materials. We don't have the time to talk about this. But one thing I really need to point out, the recycling of solid state batteries. So the question would be, will the solid components make recycling easier compared to the nowadays lithium ion batteries?
No, they won't. It's a very simple answer. So I think that if you think about it in a solid state battery, you have fusioned interfaces that have seen a certain temperature way to be able to make a connection in a solid state battery. If I just take, for instance, an oxide-based cathode electrolyte interface, I need quite high temperatures to bring it together. And I think to kind of like re-separate that and go to the components difficult. What you do normally is you just shredder the whole battery and create a black mass. And then later you give this in recycling and you do reverse mining. So you mine back the elements that have been parts of it. And that has perspective. So if I take a lithium ion battery as an example, this would be easier because I can easily strip my separator and I have kind of like my cathode, my anode side and go with that, right? So it's a little bit different in terms of the elements you have, and also the cathode and the electrolyte elements are a bit more alike, yeah, in terms of, density, whether in the periodic table of elements or closer, yeah, compared to what you find if you compare the electrolyte itself with the cathode and the anode, for instance, in a classic lithium-ion battery. The other thing that I will say here, and I think it's very important because it's something that is not discussed enough in the field currently, it is very important for recycling to find better ways to do low temperature assembly and low temperature disassembly of any oxide and sulfide-based compounds. If that is mastered, it allows you to have less energy in the separation later when you do the reverse mining. So I think it's really helpful to consider how these batteries are made. And that will affect, I think, overall in the recycling, how the refining, regaining of those components works. Yeah.
I'm very happy that researchers are aware of that field. Even 5 years ago, that probably wasn't so much the case. So I'm actually very happy that there's something happening there. On the other hand, you said it's quite complicated even within solid state batteries. Thank you very much. That was Professor Jennifer Rupp from the Technical University in Munich. Thank you so much for your time and expertise. Dear listeners, are you convinced of solid state batteries yet? Or do you remain skeptical? Send us an email at hello@batterygeneration.com or just comment below this podcast. That's it for today. Thank you so much for listening. Take care. See you next time. Bye-bye.
Thank you so much. Thank you, Patrick. It was fantastic. Really enjoyed to be on your show. Thank you.